Good day, I'm Dr. T and welcome to my office. So when we talk about chemical reactions, in the past I've mostly talked about one-way chemical reactions. These are reactions that for one reason or another, the reactants go to the products, but the products cannot react and return back into the reactants. In reality, this is the minority of reactions. Most chemical reactions can go backwards and will do so at a meaningful amount. In this case, after a while, they will establish what we call a dynamic equilibrium. Reactants are forming products, but they're doing so at the same rate as the products are reforming the reactants. Therefore, the concentration of the reactants and the products will have established an equilibrium. It's actually important for me to clarify a particular misconception. Equilibrium does not mean equal. While there are reactions where there'll be a 50-50 blend between reactants and products, those are by far in the minority. Most reactions that will establish an equilibrium, that equilibrium will predominate one side or the other. In fact, it's actually one of the important features that we like to discuss about these equilibriums. How are they shifted? What's the ratio of products and reactants? So typically we will establish K, the equilibrium constant, because of course constant starts with a K. With this, we have simply a fraction. It's a ratio. So we'll have a fraction, the product of the reactants, specifically their concentration, the product of the reactants, specifically their concentrations or partial pressures, will be the denominator, and the product of the products, multiply the concentrations of the products together, that will be the numerator. So products over reactants, and this equals K. If K equals 1, then yeah, you got a 50-50 blend. But K does not have to be 1, and rarely is it 1. If K is much larger than 1, then we are going for a reaction that's dominated by the products. If it's much, much, much larger than 1, then that's usually what we call a one-way reaction. They're not technically one-ways. No reaction technically only goes in one direction. It's just that it is so far shifted that K value is so high that it might as well be a one-way reaction. It is not unreasonable to call it one-way, even though it is technically a two-way reaction. Now, if the K is smaller than 1, then it's going to be biased towards the reactants. So obviously a little bit smaller than 1, then it's a little bit shifted towards the reactants. If it's really, really, really tiny, many zeros after the decimal point before the first number, then in that case, it's going to effectively be a one-way reaction going backwards. So you're really not going to see a reaction. It's just kind of a one-way reaction backwards. So it just doesn't take place. Now, with equilibrium, a couple other key points to point out. With this one, we're not necessarily talking about rate. Some reactions will establish equilibrium very, very quickly. Other reactions will establish equilibrium very slowly. And that's just kind of, the rate is separate from the equilibrium. The equilibrium will occur when the backwards and forwards rates are the same, but it may take a while to get to equilibrium. Or, in other reactions, it may not. It may be very, very quick. Now, once a reaction mixture has reached equilibrium, it is, of course, possible to disturb that equilibrium, to shift that so the reaction mixture is no longer at equilibrium. Now, there's a couple ways we can think about this. For starters, we could take the ratio of products and reactants and do that ratio. That will give us our reaction quotient, or Q. And Q will, of course, if it's not the same as K, the reaction will take place in order to reestablish Q, so that Q equals K. Now, in this process, we actually lead to this rather interesting scenario. Anything I do to perturb the reaction, it's going to try and undo that perturbation. If I add reactants, then that reaction is going to start going faster in the forward direction until it's reestablished equilibrium by depleting the amount of reactants that I've just added and increasing the amount of products. Now, interestingly enough, since we multiply our reactants together, if I add one of my reactants but not the other, I can actually get to a situation where by adding one reactant, I deplete the one that I didn't add. And this can be used in cases where you have one reactant that you particularly don't want. A classic remedy for cleaning up mercury spills is to add sulfur. Well, you don't add a little bit of sulfur. You add enough sulfur to make sure that all of the mercury reacts really, really well and shifts at equilibrium, so it's 100% reacted and forming mercury sulfide. And therefore, not something you have to worry about as much. You clean it up and you dispose of it properly. Now, the opposite would also take place. If I added a product, then it would shift and reform reactants. If I remove one of my products, then the reaction will shift towards the products to replenish it and reestablish equilibrium. Likewise, if I remove a reactant, the reaction will shift towards reactants to reacquire the equilibrium. Basically, it's going to fight me no matter what I do to it. And this can actually be really useful because then that can arrange things for me to control the reaction to get it the way I want it to go. For instance, the Haber-Bosch process, the synthesis of ammonia, is a reaction where the equilibrium constant is not particularly that large. And as such, you actually have a meaningful amount of reactants in with your reaction mixture. So in order to produce more ammonia, one of the approaches is to remove the ammonia, which you might as well just put it in the tanker and go sell it since that's the product you're trying to make. You remove the ammonia, and as you remove it, the reaction just keeps trying to replenish the ammonia. This is actually why you see the reaction containers containing kind of these two separate parts. The hot part where the reaction takes place and a cold part where the ammonia is removed. And this is to drive the chemical reaction forward using this ability for the reaction to fight it. Which, by the way, we refer to that as Le Chatelier's principle. A couple other caveats with Le Chatelier's principle. If it's an exothermic reaction and I increase the heat, guess what? It's going to go towards reactants. If it's an endothermic reaction and I increase the heat, it's going to go towards products. It's going to fight me. If it's a gas-forming reaction and I cause the gases to become a greater partial pressure, just adding inert gas does not help. But I cause the container to, say, shrink and squish in the gases, hey, that's increasing the concentrations. It's going to go backwards. If I've got gases on the reactants and the products, it typically goes to the direction that has the fewest gas molecules in it. Yay. So with that said, have a wonderful day, and I'll see you in later videos.